Hello everyone, welcome back to my another tutorial. This time I will talk about multiprocessing. Actually, I will show you how I use multiprocessing together with TensorFlow and how I make my YOLO implementation a little bit faster. I mean, to work a little bit faster than using a single processor. At first, this tutorial will talk about brief introduction to multiprocessing in Python, and at the end of this tutorial, I will show you how I use it to make that possible. So, first, what is multiprocessing? For new users, multiprocessing refers to the ability of a system to support more than one processor at the same time. Applications in a multiprocessing system are broken into smaller routines that run independently. The operating system allocates these threads to the processors, improving the performance of the system. As you can see in this image, on the left side is multiprocessing used, and at the right side it's not used. And as you can see, left side does the job 4 times fast. So you already know why multiprocessing, but if there is still a question, you should consider a computer system with a single processor. If it is assigned several processes at the same time, it will have to interrupt each task and switch briefly to another to keep all the processes going. However, the default Python interpreter was designed with simplicity in mind and has the thread-safe mechanism, so-called GIL. In order to prevent conflicts between threads, it executes only one statement at a time, so-called serial processing or single threading. This is how our usual Python script works. We do tasks linearly. In this tutorial, we will see how we can spawn multiple subprocesses to avoid some of the GIL's disadvantages. So, the multiprocessing module in Python standards library has a lot of powerful features. If you want to read about all the tips, tricks and details, I will recommend using the official documentation as an entry point. You can find it on Google. In this tutorial, I only will show concrete examples that are related to my YOLO object detection tasks. So there will be 2 parts. First will be about multiprocessing communication between processes, and second will be using multiprocessing with YOLO object detection, the preprocessing and post-processing. And at first, I will talk about quick use. An effective use of multiple processes usually requires a communication between them, so that work could be divided between processes and the results can be aggregated. Multiprocessing supports 2 types of communication channels between processes, quick view and pipe. At first, I will talk about quick view, then pipe, and we'll compare them. If you have basic knowledge about computer and data structure, you probably know about the quick view, that there is first in and first out. Python multiprocessing module provide a quick view class that is exactly that, data structure. They can store any Python object through simple ones or bests, and are extremely useful for sharing data between processes. Quick views are especially useful when passed as a parameter to a process target function to enable the process to consume data. By using put function, we can insert data to the quick view, and using get, we can get it item from quick views. Here I will show you, I'm showing you a simple script where I already wrote a very simple code, and with this code we start 2 processes, one that puts data to quick view and one that picks. As you can see, functions are respectively named. Right now, my goal is to check how long it takes to put numbers from 0 to 1 million into the quick view and then read it. And we can run this function from the terminal. CD desktop and then Python multiprocess. And it should take us few seconds to finish its tasks, and as you can see, it finished task in 7.5 seconds. But this was quite simple data. So because we'll be working with images on my YOLO detection, let's try sending 100 random images between these following functions. Let me copy another function. So here it is another script. I copied it from my GitHub repository, and as you can see, it already generates 100 NumPy random images and puts them to QQ. So let's run this and let's see how long it will take. So as you can see, because there isn't a lot of data, it took only 0.7 seconds to finish this quite simple task. And that's it. Now let's move to a pipe. So a pipe can have only 2 endpoints. Hence, it preferred over the QQ when only two-way communication is required. The multiprocessing module provides pipe function, which returns a pair of connection objects connected by a pipe. The two connection objects returned by pipe represent the two ends of the pipe. Each connection object has send and receive methods, among others. Same as before, I used the same functions to modify them to make from QQ to a pipe, and all these functions you can find, of course, on my text version tutorials. I will post all links to them and you can check what are the differences. So again, I will copy these from my gist. Same as before, at first we'll do with 1 million parameters with simple data so that we could compare the results of pipe and QQ. It will take a few seconds. As you can see, pipe did the job in 3.6 seconds. It was almost twice faster than a QQ. Same as before, because we'll be working with images, let's test sending 100 random images to the pipe. Again, different code. Let me copy it. As you can see, size is the same, by 416 by 416 and so on. And let's run this multiprocessing. So we have all the results we want for now, and we now compare them. So for comparison, I'm not going to use same results because I already tested this before. My processor was doing something different and it did the job in different times. So right now my results will be a little bit different, but when we compare them, they are quite the same, proportionally quite the same. So I can show this to you. Simple data was numbers lists in range from 1 to 1 million. NumPy data was 100 images of 460 by 460 by 3 of shape. The results were quite interesting, and it's hard to say why they were so. While we were sending simple data to pipe, it was around 40% faster than using QQ. But when we were sending random image and the same way, QQ was faster by around twice and by 50%. I can't answer why there is such a difference between the results, but anyway, I don't really matter. I simply gonna choose a method depending on my data type. So as you can see, because for some reason sending NumPy images through a QQ is a little bit faster than using pipe, I will choose pipe. But if you would be sending very simple data, as I showed that are in range from 1 to 1 million, you should prefer using pipe because it's a little bit simpler. So now I'll talk about second tutorial part about YOLO object detection and preprocessing and post-processing with multiprocessing. So usually we want to use multiprocessing to make tasks finish faster. In my YOLO object detection implementation, this is relevant for a few methods. So when we would like to use it for video detection, real type detection, and object tracking. It's not relevant for use for image detection because usually we do it one time and that doesn't take much time. But for other methods I mentioned, multiprocessing can save us a very large amount of time. While using multiprocessing in real-time tasks, we might get more frames per second and much smoother results. So I will work on the video detection process. This process we can apply for both video or real-time detection. because steps are actually the same, only the source is different. I drew a process how it looks right now when we execute one function at a time while processing a video record in single processing. As you can see, we at first calculate video frames, and we must have these frames where we want to detect objects. After detection, we must post-process detection results. Then we draw results. That's a bounding boxes on a frame. Then we can show the processor frame and do some steps with the next frame. We do this loop until we reach the last frame. Problem. Usually we use multiprocessing for math tasks, where we can divide calculations to the process. But now it's harder because we can only do the next step if our previous step has finished its job. Although YOLO detection takes most of the time, around 80%, and we can't do anything with that, except we would have several GPUs. But usually no one has, actually. So my idea was to divide each of these functions to each process. This means that YOLO detection will be not waiting for other tasks to finish their job. So it's hard to explain. So again, I drew that what I mean. Actually, this will be not a real parallel process, but this is the best I could find in this current task. As you can see, each process has its own results quick view, which is necessary to share data between different processes. To achieve this kind of result, I took my single process video detection function and divided it into smaller functions. I will not share this testing code, how I did this, how I measured this, but actually I'll post a link on my text version tutorial where you can download a utils.py file which I used to measure these differences. Here is the code, and I call this function detect video real time in multiprocess. Here is all different functions which I used to do detection with multiprocessing. So I'm not going to talk line by line about details, it's just an overview if it's worth changing code into parallel process. So to compare everything, I will check how long it takes to process a video without multiprocessing and with it. Also, I know that most of the time takes YOLO detection, so we'll try to take this into evaluation. Pick to make test with a YOLO V4 model with 460 by 460 input size. My CPU is i7 6700K and I have 1080 Ti GPU. Also, I use a TensorFlow which is converted to FP32 precision model to keep the same accuracy as the original model. To get the results and make them comparable, I had to modify my original utils.py file function, which of course, as I told you, will be able to check in a different link on my text version tutorial. All in all, I will be measuring two time parameters: YOLO detection time and total time to process the whole video. To make detection comparable, I'm starting to count start time after the first image is detected, because we don't want to measure the model loading time. Of thought, loading the TensorFlow model takes 3-4 times longer than the TensorFlow model, so we must take model loading time into consideration. So right now, let me see what are my configurations, configs.py, and right now it is TensorFlow model, YOLO custom weights false, and yeah, okay, that's fine for me. And where's my detection demo? So right now it tests MP5 file video. We have this kind of file, and I need to uncomment these lines, detect video, if I would like to check it out. Let me see, detect video, where it is. And so here it will print the whole duration, and start time is here, start time, and actually it starts when the first detection frame appears. I mean, our model starts. So I of course can run this. Let me see what GPU I use for this kind of task. It's first, and okay, I can actually run it. Python, and of course I will not show results because it also might take a little bit slower when results are shown. So I'll write simply Python detection demo.py, and it will start, and we'll wait for task to finish. So it finished, and as you can see, this is my total duration. I will copy it somewhere here. This is without multiprocessing, and right now I will use different functions. And you might ask why I don't use load YOLO model here. Well, actually, when using a multiprocessing, there is a trick you should do, is that you should load this model within the process where you do these detections. So I'm using load YOLO model somewhere else, actually here, in a new spawn process. So otherwise you get some kind of error, and I didn't have time to solve these things with a graph, sessions, and so on within TensorFlow 2. I know this better in TensorFlow first, but because we are using second TensorFlow, I didn't waste the time for that. If you know how to solve this, you can write an issue on GitHub and let me know. We'll see, maybe we can fix this. So we'll test right now with multiprocessing detection demo. Again, it will take a little bit to finish its tasks. So as you can see right now, I have a result of multiprocessing, and at first look, it might see that it's not worth of using multiprocessing actually, because total duration was even longer by 1 second, and detection time is much slower. So why I should use this, you might ask, but actually, if you don't have a GPU, yeah, you don't need to use. If you have GPU, well, yes, you don't need to use it. But if you have GPU and you know how to convert this model to TensorRT, yes, you must use it. So because I'm not going to show these results right now, or I do. Well, actually, I do can. So let me change some configurations. TensorRT, I already converted this to FP32, and yeah, it should work actually. And let's run it right now. And let's see what are the results. If you remember my previous tutorial where I did a comparison of TensorRT and simple TensorFlow model results and frames per second comparison, you might remember that that's amazing difference. But the main disadvantage is that TensorRT model takes much more longer to load this model to make it process a whole video. But if you have for very long video, it's totally worth to do that. So actually, let's wait for results and we'll talk about later. So it finished doing its job, and as you can see, here is the difference. And one more test left is to use the same without multiprocessing. So let's run this. If you're interested, let's see what we can get with it. So it finished, with detection video on TensorRT, and it's kinda something strange here, and the results shouldn't be that kind of difference. So I'll run it again. Maybe there was some kind of mistake, and we'll come back, but the results might be different because I'm recording, but maybe, who knows, maybe not. So let me run it again. So again, second time was not lying to me, but still there's something real strange because, well, as you can see, multiprocessing didn't improve that much as I expected, but as I told, might be because I'm recording. So actually I will stop our recording and I'll measure this again, and then I will show you a table with our results. So because recording takes a lot of CPU processing for high quality recording, and well, you understand this. So anyway, let's see later after I test this by myself while not recording. So see you a little later. So I made a testings without recording, and results are shown in this following table, which I filled up and I'm showing right now. So first, let's discuss about TensorFlow YOLO v4 results. As you can see, while not using multiprocessing, detection time was 23 seconds and post-processing time was around 7.73 seconds. While using multiprocessing, detection time was slower by 4.42 seconds, but post-processing was faster by 5.35 seconds. That's around 3 times faster, and that's around 325% improvement. But comparing the final result, it's only 3% faster. I think that even if I was using a GPU, TensorFlow still requires a lot of CPU resources. And while we are using CPU for post-processing, detection gets slower because of lower free CPU resources. Although in my previous tutorial we were comparing results of TensorRT and TensorFlow, so I decided that it should be interesting to see its results in multiprocessing also. So comparing detection time, there was also no degradation for detection speed. It dropped only by 0.86 seconds, but post-processing didn't improve that much as with the TensorFlow model, only twice. But while seeing the final results, we can see that improvement was 24%. That's a much better improvement than with the TensorFlow model. So, results with TensorRT were much better. It seems that the compiled frozen model requires less CPU for detection than the TensorFlow model. Also, it's more than twice faster. So, if you have GPU, I recommend only using TensorRT models for your final projects. For development, you can use TensorFlow because it's faster to debug and do modifications. The goal of this tutorial was to measure if there's gonna be an improvement in time while using multiprocessing. The final results tells us, yes, it's worth implementing multiprocessing. Codes get messy and it's hard to debug, but if you need at least a few % of improvement, it's worth trying and doing so. But if you like a clean code and easy to debug code, yeah, you can stay on the same single processing. Now, while I have a positive results, I will try to use multiprocessing in my future projects. See you in the next tutorial. Hope this was useful for you. You can share this tutorial, like my video, and of course, comment if you don't understand something, and see you in our next tutorial. Don't forget to subscribe. See you next time. Bye.